all hear me?
Yes, sir, we can hear you.
Yes.
Okay, so first of all, I would like to thank Dr. Kamal and the student chapter of to make a presentation on the testing of piles and the interpretation of data. So without taking much time, let me have the sharing rights.
Yes, sir, we are allowed sharing option.
Okay, right, I can. So let me close the video because it interrupts with the sequence. Right. Okay. So today I'm going to discuss on the testing of piles and interpretation of test data. So this is actually a very important topic because as you may know, the piles of the pile failures are actually attributed to construction related issues rather than the design or other types of issues. So therefore, it is very important to test the piles because when we talk about the board and cast in situ piles, there is no way of checking the quality of the pile before it is installed. So we need to verify that the pile is having the sufficient integrity and it can take the load. So those aspects need to be integrity testing is carried out to check whether there are any defects uh, during installation or after installation, to check whether there are any effects along the pile. Uh, and there are several methods available to check the integrity testing. Then I would like to discuss about the compression load test. And there are a large number of conventional static load tests are IML, the instrumented pile load tests or instrumented main load test, maintain load test. So sorry for the disturbance. I think the capacity exceeded and I was removed from the list. So let me continue from where I stopped. Right. So this is what I was discussing. So I'm going to talk about the integrity testing, the static load testing, conventional and advanced type of static load testing and the interpretation. Then high strain dynamic load tests, right? Lateral load test, and I'm going to talk about lateral load testing and tension load testing as well. So first, I would like to discuss on the testing strategy and the frequency. So there are certain guidelines on the testing frequency. So generally speaking, if no proper investigation has been carried out, and if the piling work is carried out in the complex or unknown ground conditions, the risk levels are categorized as high. So in such cases, it is recommended to carry out preliminary pile tests, right? This is actually ultimate load test, the testing of piles are until failure. So one preliminary pile test per 250 number of piles. Then one working pile test per 100 working piles. So this similarly for other, if the testing data are available and the ground condition is more or less investigated, and the construction company has experience in constructing piling in this similar type of conditions, the criteria is relaxed. So for example, if the risk level is low, that means the contractor has already had experience in piling in similar ground conditions. So then in such case, one preliminary pile may be tested for 500 piles and one working pile for 100 piles. So likewise, some guidelines are available for the testing frequency of high strain dynamic load test as well. Usually 2% to 5% of the total number of piles are recommended to be tested for high strain dynamic load test. So this is actually the 2% to 5% of the working piles, right? Or minimum 2 number of piles to be tested. According to the Sri Lankan guidelines, CEDA guidelines, this is the CEDA guidelines. So integrity tests has to be carried out for all the piles. Then high strain dynamic load test should be conducted for 5% of the total number of piles. And it is recommended to conduct 1% of the total number of piles for static load test, MLTs. Okay. So this is the strategy for the testing frequency. Then if I talk about the integrity testing, so integrity testing is basically carried out to check the quality of the construction quality of the pile. We can broadly categorize integrity testing into two: intrusive methods and non-intrusive methods, right? So intrusive method means you're basically drilling a core through the pile to inspect the quality of the core. So this is actually creating a hole through the pile. It will slightly affect the pile integrity. Later we can grout the core using cement grout and seal the core. And coring is expensive and time consuming, but if there is a serious defect, we can use the core to rectify the defect as well. Then comes less expensive methods, non-destructive methods. The non-destructive methods can be broadly categorized into surface reflection method and direct reflection methods. So in this testing procedure, what we basically do is we will send a sound stress or ultrasound wave through the pile and detect the reflection, right? Reflection of the wave. And by looking at the reflected wave profile, we can make various predictions regarding the integrity of the pile. So under surface reflection methods, there are pulse echo method. This test is actually commonly known as PIT. So PIT means pile integrity test. So there are a large number of pile integrity tests, but PEM is the most widely used pile integrity testing method in Sri Lanka and worldwide. So therefore, this is commonly referred to as PIT. You can hear me, right?
Yes, sir, we can hear you.
So the transient dynamic response method is not very common. So it is an advanced version of pulse echo method. Then comes the conventional high strain dynamic load test. This is commonly referred to as PDA. PDA is actually referred to pile dynamic analyzer. This is a commercial name given for a testing procedure. So, but the technical term is high strain dynamic load test. So I would like to discuss about the high strain dynamic load test as well. Then comes direct transmission methods. So in the direct transmission methods, we need to plan in advance. So water-filled tubes are installed during the construction of the pile, and these water-filled tubes will be used for testing the integrity. Right. So direct transmission methods there are several methods: parallel seismic testing, cross-hole sonic logging, single-hole sonic logging, and the CT, cross-hole tomography. It is an advanced version of the cross-hole sonic logging test. So these tests are widely used as direct transmission methods. I will talk about these tests in detail in the coming slides. So for parallel seismic testing, PST testing, you need to drill a borehole adjacent to the pile. And cross-hole sonic logging requires 2 or more number of tubes to be installed during the construction stage of the pile. The single-hole sonic logging is a simpler version of cross-hole sonic logging. In this test, only one tube is used for the testing. So this is applicable for relatively small diameter piles. So let me discuss one by one. First, the intrusive method, coring through the pile. So coring through the pile is usually done only if the other test indicates a serious defect. So like direct transmission method or surface reflection methods indicate some integrity issue, serious integrity issue, then to further investigate the problem, location, the extent, and so on, we can carry out coring, right? For small diameter piles, 1 or 2 cores may be sufficient. But for large diameter piles like 1500, 1800 diameter piles, maybe 3 or 4 cores are needed. So this is one example of coring for a defective pile. So in this case, it was planned to drill 4 cores, location 1, 2, 3, 4. But during the drilling of one location, location 2, rebar cage was encountered. So the coring could not continue below a certain depth. Therefore, it was decided to drill another hole here. Then once the defect is identified, this cores can be used to rectify the defect. So that is one of the biggest advantage of coring through the pile. But it is time consuming and expensive. It is usually conducted as the last resort, right? If other methods indicate a serious defect, then only we will do this to rectify the pile. This is an example of core taken through the pile. You can see concrete core. some brakes are actually mechanical brakes. During coring, the concrete breaks, and it may not indicate a break or a defect along the pile. But this is a clear defect, indication of a defect. You can see at a certain depth, 26-meter depth, an intrusion of soil plus bentonite, like this part. Here, this is another core taken from another pile. You can see fractured concrete, so indicating low quality concrete along the pile. So these defects have to be rectified. Then let's discuss about the other pile integrity tests, right? Non-intrusive methods. So pile integrity is quantified by using a parameter called beta. So beta is defined as the pile impedance ratio, Z1 or Z2. Z is the pile impedance. The definition of the pile impedance is given here. Pile impedance is defined as AE over C. So A is the cross-sectional area of the pile, E is the elastic modulus of the pile material, concrete, and C is the wave velocity. If there is a serious quality issue, then pile impedance will be affected. So usually the pile impedance will be reduced due to the presence of a serious defect. So as a result, this impedance ratio means Z1 is the impedance of the defective section, and Z2 is the nominal impedance of the pile shaft without any defect. So this ratio will become less than 1. So based on the value of beta, we can classify the damage, right? If the impedance ratio is close to 1, there is no damage. Pile has uniform cross section. So if the beta value is between 0.8 to 1, there is a slight damage. Likewise, the damage can be classified by referring to the impedance ratio. Right. So pulse echo method is commonly referred to as PIT in Sri Lanka. So in the pulse echo method, a hammer is used to send a stress wave through the pile, and the reflection is detected by a transducer. So we can use an accelerometer, a geophone, or any relevant transducer to detect the reflected wave, right? So when you send the wave, if there is no defect, it goes to the pile. Sorry, I am getting disconnected time to time. Let me continue. So let's say you have a pile with a free end. Free end means there is a soft toe condition, right? Fixed end means pile is resting on good end bearing strata, right? Like maybe fresh rock or something. And let's consider another case where you have a defect along the pile, right? This is necking. It's a reduction of the pile diameter. And this is another issue where you have a bulging, right? Enlargement of the pile diameter. So this is actually it's a defect, but it will not affect the pile integrity or capacity. So in these 4 cases, let's see what will happen to the reflected wave. So if you have a free end, and this is the wave profile, this is the direction of the particle velocity. It can be either you can take the sign convention and convention in whatever the way you want. So in this case, the negative side is taken as the the direction, negative sign is taken as the direction of the initial wave. So if you have a response, right, this is the reflected wave from the pile top. So if you have the reflected wave also in the same direction as the direction of the initial the wave, so this is indicating that there is a tensile response at the pile toe, right? Pile toe. So as a result, you will see an increase in the velocity, particle velocity due to the free end. So if you have a fixed end, then what happens is wave propagates, right? Particle velocity is initial velocity. Let's assume that it is in the negative direction. Then the particle will, the wave will propagate and it is reflected back as a compression wave, right? And as a result, you will see a response in the direction opposite to the initial direction of the wave. So this is indicating that the pile is resting on firm ground. Similarly, if we apply the same concept to this pile, so let's say you have a free end. So free end means the response from the toe should be in the same direction as the initial wave. And there is another defect, necking. So necking will again send a reflected wave in the same direction as the direction of the initial wave. So if you have this kind of response, this is indicating some kind of defect in the middle of the pile. So if you have bulging, then the bulging will send a compression wave, right? This will send a tensile wave. So due to this, the bulging in the enlarged area, this zone, a compression wave will be reflected. As a result, you will see this type of response. Then from when the wave goes to the toe is free, right? Toe is free means it has a soft condition. So you will see this kind of tensile response, a response similar to the initial wave. So by looking at the direction of the response, we can predict the integrity. We can get an idea about the integrity of piles. So if I apply this to real the records, so this is the reflectograms obtained from the pulse echo method, real test data. And if you have a pile having a cross section like this is the initial peak, and these are the other peaks. So you have to look at the direction of the initial peak. It's in the positive side in this case, and the reflected wave, right? You can see these peaks have a direction opposite to the direction of the initial peak. So this is indicating a bulge along the pile shaft. And this is in the same direction as the initial peak. It is indicating a soft condition at the toe. So it is sending a tensile wave, right? So this pile has a serious defect somewhere in the middle, necking. So because of this, it will send, right, a tensile wave, reflected wave, tensile wave. As a result, you will see a reflection in the same direction as in the direction of the initial peak. So if you have this kind of response, that is indicating a defect, right? And you will see some multiple defects along the pile, which is reflected by the wave response. So then by looking at the reflectogram, we can interpret the integrity test data as shown in this the pile classification chart. So pile classification AA means sound shaft integrity. That means there is a clear toe reflection and no serious defect along the pile. So AB means no major defect indicated, right? That it may not be perfect, but no major defect. So ABX, no major defect indicated up to a depth X. So PF means there is a flow at an approximate depth F. I'll show you some examples. Then PD means there is a defect, right? Then inconclusive records up to depth below depth X. IVX means inconclusive record below depth X due to some disturbance to the wave. Then IR means the entire record is inconclusive. So likewise, depending on the results of the PIT test or pulse echo method results, we can classify the integrity of the pile as shown in this pile classification chart. So by referring to this chart, let's try to classify these reflectograms, right? So these are reflectograms obtained from the PIT tests, so pulse echo method tests conducted on piles. So this is indicating the length of the pile, right? The dark line is indicating the length of the pile. So you can see this is the initial peak. This is the initial peak, and all the other peaks are in the direction opposite to the initial peak, below the zero line. And here you will see some part of the reflectogram is going above the zero line. It is indicating, we call it a flow, right? So this pile can be classified as PFX. There is a flow at a depth below depth X. Then if you go to B, right, and we can interpret the condition of the toe as well from A. So toe, actually the toe reflection is in the direction opposite to the initial direction. That means the pile is resting on sound strata, maybe hard rock or some very good dent bearing strata. So that is why you will get a response opposite to the initial response. Now, if we look at pile B, no defect, right, can be seen. So this is the response of the initial wave, and at the pile toe there is a reflection in the direction opposite to the initial reflection. So this is basically indicating a good quality pile without any integrity issue. So it can be classified as AA. Then pile C, you can see this is the length of the pile. So before the wave reaches the pile toe, you can see various peaks in the direction similar to the direction of the initial peak. So this one, that one, and this is also indicating a soft toe condition. So you can, this pile has multiple defects, right? So it can be classified as PDX. D. So pile D, so no major defect is encountered. So it can be classified as as AB. Similarly, E, no defect. So it can be classified under AA. Then F has multiple defects. Then G, you can see close to the pile toe, you can see a response in this direction similar to the initial response. This is indicating some flow along the pile. So it can be classified under PFX. And pile H has multiple defects, right? You can see peaks, multiple peaks in the same direction as the initial peak. So this is indicating a defective pile. So likewise, by looking at the reflectograms obtained through pulse echo method, we can interpret the integrity of the pile. So if the piles are very long, usually piles having lengths greater than about 30 meters, sometimes we cannot see a clear toe reflection. So after some depth, the wave becomes almost flat. So in such case, we cannot predict the integrity of the pile up to the full depth, right? So this is happening for long piles. But for these piles, we can clearly interpret the integrity and the toe condition. So these defects can be detected through the integrity test. So toe condition, any intrusions, cracks, joints, multiple defects, diameter changes, necking or bulging. If any difference in the layer, subsurface layers can also be detected, because this, if I go back to the reflectograms, this can be due to the presence of a weak soil layer, right? This can be due to the presence of a weak soil layer, and maybe along this, up to this length, the pile is passing through hard layer, and suddenly there's a weak layer. As a result, there's a tensile response up to a certain length. So this is basically an indication of the presence of a weak layer. That is why it is classified as a flow, right? So likewise, you can make various interpretations, predictions about the integrity of the pile. So these are non-detectable defects. So we cannot detect these issues through the integrity normal PIT tests. Gradual increase or gradual decrease in the pile size cannot be detected. That if the pile is curved or misaligned, we cannot. Small intrusions may not be detected by the wave, right? The loss of cover cannot be detected through this. And the presence of the debris. If there is a soft toe, then it may be possible to detect, but for very long piles, as I said earlier, you may not be able to detect the toe reflection, right? So it has its advantages as well as limitations. Then let's discuss about the cross-hole sonic logging. This is a direct transmission method. If we are planning to do cross-hole sonic logging test, we have to plan in advance. During the construction stage, you have to install either PVC or steel tubes. So these are the tubes with you can see end caps. We need to fill these tubes with water before or immediately after concreting, or before concreting you need to fill this with water, otherwise debonding will occur. These tubes will be debonded from the surrounding concrete, and your wave response will be affected. So these tubes are attached to the rebar cage, right? And the number of the tubes depends on the diameter. So as a rule of thumb, each 300-meter pile diameter needs one tube. So there's a minimum number. 3 is the minimum number. Okay. So minimum 3 tubes are needed. But as a thumb rule, for each 300 millimeter diameter, you need one tube. So that means if your pile is having a diameter of 1.5 meters, you need 5 tubes, minimum 5 tubes, right? So that is the thumb rule. 38 millimeter to 50 millimeter, either PVC or steel tubes are used, right? So generally we are using 38 millimeter tubes. And this test method has been standardized under ASTM standards. So PVC tubes are very popular in Sri Lanka. Sometimes steel tubes are also used. In the STM guidelines, steel tubes are preferred over PVC, but according to the local experience, PVC tubes give less noise and high level of energy. So the better signal response is detected if PVC tubes are used, right? So these tubes must be filled with water before concreting or immediately after concreting. Otherwise, debonding will occur, right? So after the tubes are installed and the pile is cast, we can conduct the sonic logging test. So what we do is we lower the the two probes. One is the okay. So this is sending the ultrasound wave, and the receiving probe will receive it, right? This data logger will record the wave arrival. Okay. So we will lower the receiver and the transmitter to the bottom of the tube and start lifting them at the same time while maintaining the same elevation, right? While sending waves. So slowly, this both transmitter and the receiver is slowly lifted while sending the wave. And this test can be conducted in this manner. So here you place the transmitter and the receiver, and the waves are sent between this tube and the second tube. So likewise, you can continue doing the test for different tubes, right? As shown in the arrow. So arrow is showing the direction of the wave. Here you have the transmitter, there you can have the receiver and detect the wave propagation. Okay. So this is what is measured by the recording system, data recording system. So it is recording the wave arrival. So the transmitter is sending the wave and receiver is detecting the wave. So there is a time gap, right? It is called the first arrival time, FAT. This is detected. So if there is a defect, right? If there is a defect, the arrival time will be affected. Okay. So you will see a delay in the arrival time if there is a defect, right? So we are taking this continuous records of FAT arrival times while lifting the two transducers like this. And we will try to maintain the same elevation while lifting them, right? And we can plot all the wave records in one diagram. It is known as the waterfall diagram like this. So here you can see a diagram representing something like a waterfall. So this is actually, it includes overlapping wave records like this type of records. And here you can see a gap. This is the arrival time, right? Arrival time along the pile. So if there is a defect, there is a loss of signal or delay in the arrival time. So in this case, this particular case, no defect, serious defect is recorded. Let's look at a pile, a waterfall diagram of a defective pile, right? So this is the waterfall diagram obtained from by sending waves through 1 and 2, right? The wave transmitter is at hole number 1, receiver is at hole number 2. So when you start sending the waves between 1 and 2, this is the record. And you can see a loss of signal. This is indicating a delay in the arrival of the wave, right? So it is indicating that there is a defect at a depth of about 28 meters. between 1 and 2. Similarly, between 2 and 3, this is between 2 and 3 also, you can see a defect, right? Approximately at the same depth, 3 and 4, 4 and between 4 and 1. Likewise, in all 4, all 6 records, you can see a defect, almost at the same level. So this is indicating an area-wide defect, right? Area-wide defect at a depth of 28 meters. So this needs to be rectified. So once you detect this kind of defect along the pile, it is a must that you need to drill some course, right? Concrete course, and rectify the pile by grouting. So this is where you need to do coring, right? Once you encounter this kind of area-wide defect. So there can be some localized defects. Let's say, for example, between 1 and 2 and 2 and 3, 1 and 3. These 3 may indicate a delay, but other piles, the waterfall diagrams may not indicate any delay, right? So in such case, there is a localized defect in the region demarcated by hole number 1, 2, and 3. So likewise, we can interpret the area of the defect by looking at this waterfall diagram, right? Then the single hole sonic logging. In the single hole sonic logging, only a single hole is drilled. This is actually done for usually for small diameter piles. So both the transmitter or the source or the transmitter and the receiver are connected to the same the cable, and the transmitter is sending the wave and it is detected by the receiver. So you can lift this first. You can bring this all the way to the top of the pile, toe of the pile, then start slowly lifting it while sending the wave. So you will see this kind of waterfall diagram again. So if there is no defect, so it must indicate the same wave arrival time, because the length between the receiver and the transmitter remains the same. So if the concrete quality is uniform, then the wave arrival time should be identical along the depth. But if there is a defect, then there is a loss of signal or a delay in the arrival, like this. So this is indicating some kind of defect somewhere in the middle, right? Somewhere here. Then this cross-hole tomography is an advanced technique utilizing the same the cross-hole tubes, right? So this is done to get a either 2-dimensional or 3-dimensional visualization of the defect. So once you detect, as I said earlier, if you have an area-wide defect like this, you can drill holes and rectify. But if you, let's say you have a localized defect or multiple defects, then in such case, it is important to have an idea about the extent of the defect. To quantify, you need to quantify the size of the defect. So in that case, we can do this cross-hole tomography. So in the cross-hole tomography, what we do is the receiver is fixed at a certain point, fixed receiver, and we will move the source, right? We will move the source and start sending waves like this. So multiple wave records are taken. Then by changing the location of the receiver, we keep doing the same thing. So thousands of wave records are taken like this, right? So we have the wave arrival times for each of this location, receiver location, This is the location of the receiver. This is the location of the transmitter source. So we have multiple wave records. So after taking this kind of multiple wave records, we can, by using a computer software, we can obtain a three-dimensional image of the defect, right? Like this. So once you identify the extent of the defect, it's very easy to plan the rectification methods. You need to drill holes up to the defect and grout the defect, seal the defect, right? So for doing that, you need to first identify the extent of the defect. The concept is very simple. Now, what the software does is, it will, this is, let's consider a one wave record. This is the borehole, one hole, right? One tube, where you send the transmitter source. And this is the other tube with the receiver. And this is the wave record, right? You know the wave arrival time. So what the software does is, it will discretize this area between the tube number 1 and tube number 2, let's say, into large number of squares like this, regions like this. Okay. Then we can assume the wave velocity through each segment. So by assuming wave velocities through each segment, we can calculate the arrival time, right? Arrival time, you simply using S equals UT. U is the assumed velocity. Then the velocity is actually, we don't know what the wave velocity is. But by using multiple wave records, right? Multiple wave records gives a large number of simultaneous equations with different velocities for each segment, right? So for this particular segment, let's assume that the wave velocity is V1, this segment V2. Likewise, different segments might have different wave velocities. If there are no defects, the wave velocities are uniform. But if there is a defect, then there can be a different wave velocity, right? So we assume wave velocities through each segment. Then by using the multiple wave records, wave arrival times, and you can have large number of simultaneous equations. Then by solving these large number of simultaneous equations, you can fix the velocities. Okay. So once you get the velocities, it will show as a velocity profile like this. So you can see small squares, right? Small squares indicating this kind of segments. So each segment, once the analysis is done by using multiple wave records, you can calculate, the software can calculate the wave velocities for each region like this, right? So low velocities indicate a defect. Low velocities indicate a defect. So this is the principle behind the cross-hole tomography, right? And once you have multiple wave records, the software is capable of creating this kind of three-dimensional image with wave velocities, right? And the lower wave velocity regions indicates the defective region. So that is the concept behind cross-hole tomography. Then parallel seismic testing. To conduct parallel seismic, this parallel seismic testing is not used generally for identifying the defects. We can identify the defects, of course, but this is generally used to get an idea about the length of an old pile foundation. So let's say you have an old building which is constructed on a pile foundation, but you have no record of the length of the pile diameters, and so on. So we have no record. So you need to do some add some additional flows, so to do some repair work or whatever. You have to have an idea about the condition of the existing pile foundation. So in such case, this parallel seismic testing comes handy. So we need to drill a borehole, right, adjacent to the pile to be tested. This is the pile to be tested. Already it is integrated into the superstructure, right? Old pile foundation. So we drill a borehole, then you give a hammer blow, and the wave is detected using this the receiver, right? Receiver probe. So wave will go along the pile and it enters soil and it is detected by the receiver. Okay. So it is better to drill this borehole as close as possible to the existing pile foundation. Right. This is actually a borehole, and better to have a casing, right, to stabilize the hole, and it has to be filled with water. So a typical record is shown here. So you can see when you move the receiver, it detects the wave arrival, right? So the wave propagates through the pile and it enters the surrounding soil and detected by the receiver. So you can the seismograph will detect the arrival time, and when you move the receiver to the bottom of the borehole, you will detect an increase in the arrival time, because the wave travels along a longer path, right? So you can see a gradual increase in the arrival time like this, and if there is a defect, you will see a loss of signal somewhere in between. So this response actually indicates a defect-free pile. And when the wave starts moving below the toe of the pile, you will see a change in the gradient of this response. So if there is a sudden change in the gradient of the response, that is indicating the toe of the pile, right? So by looking at this wave response, we can get an idea about the length of the pile. And if there are any defects, the defect also can be detected, right? This is parallel seismic test. Then I would like to discuss a little bit on the latest advancement in pile integrity testing, that is called thermal integrity profiling, TIP test. So this is basically, it has a lot of advantages. That is why I thought of discussing it in this forum. It is not yet widely available in Sri Lanka. The test is available in Sri Lanka, but it's not very popular in Sri Lanka. But in the countries like United States, it has become a standard response procedure. It is standardized as well. So if before going into the TIP test, thermal integrated profiling, let me briefly discuss some advantages and disadvantages of cross-hole sonic logging, because this test is basically compared with cross-hole sonic logging test. So advantages, we can detect the quality of the concrete within the cage, right? And we can incorporate cross-hole tomography to get an idea about the extent of the defect, 3D visualization of the defect. So those are advantages of the cross-hole sonic logging. And there are limitations or disadvantages. So we need the access tubes. And you have to wait for some time Generally, we need to wait for about 7 days before conducting the PIT test or sonic logging test. At least 3 days waiting time is needed until concrete has a sufficient strength. And it cannot assess any issues outside the rebar cage because these tubes, access tubes, are fixed to the rebar cage. So if there is a concrete cover loss or something outside the cage, this cross-hole sonic logging cannot detect, right? And debonding or bleeding issues can significantly affect the interpretation, right? And it can sometimes lead to unnecessary coring. So to give you an idea about the limitation of the cross-hole sonic logging test, let me explain a test conducted in using this cross-hole sonic logging test. So here you can see CSL tubes. These are the cross-hole sonic logging tubes fixed to the rebar cage, and they have created a defect, artificially created a defect outside the rebar cage using this foam, rigifoam material, right? And the pile is concreted, so there is a defect outside the cage. And cross-hole sonic logging test is conducted, but it cannot detect the defect, right? According to the cross-hole sonic logging test, this is a defect-free pile, but actually there is a defect outside the cage, right? Then in addition to that, so you may get this type of wave record if there are debonding issues. So debonding means PVC tubes or steel tubes are debonded from the surrounding concrete. This can happen if you forgot to fill the tubes with water, okay, before concreting or immediately after concreting. So then this is the same pile. They after detecting this kind of debonding issue, they have removed the tubes and retests after removing the tubes, and you can see a very good wave response. So no defect, but along the pile shaft, but there are debonding problems. Then comes bleeding issues. Bleeding means around the tube, water can accumulate, right? Water is separated from concrete, and that water can accumulate around the access tube, creating this kind of bleeding problems. So actually bleeding is not as, it will not, it will indicate as a defect along the pipe. So because of, due to these issues, sometimes the cross-hole sonic logging test can create problems. Therefore, thermal integrity profile test is developed to overcome these limitations. So in the thermal integrity profiling test, commonly referred to as TIP test, thermal wires are fixed to the rebar cage. So the wires, there are two methods actually. One is this method. This is known as the method B, where you fix the wires with thermal sensors to the rebar cage. So each wire has a thermal sensor. It can detect the temperature, right? So you know that during the concrete curing, the heat of hydration is happening. So this heat of hydration increases the temperature of the pile. So this increase in the temperature of the pile can be detected by these sensors, these thermal sensors. And that temperature reading can be used to interpret the integrity of the pile. So that is the basic concept. Okay. So there are two methods. This test is standardized under ASTM D7949, right? It's a standard test method now. So if I explain the concept again, so this is the heat of hydration, and these are the sensors, right? Sensors. So if the two sensors, the heat of hydration is maximum at the center of the pile, right? Center of the pile, you will get the highest heat of hydration temperature, and when you go to the edge of the pile, the temperature slowly decreases, right? Gradually decreases. So if the two sensors, the sensors are fixed to the rebar cage, if the two sensors, right, are fixed at a distance equal from the center, then both sensors must detect the same temperature. If one sensor is detecting a higher temperature, that means it is close to the center, right? So at the same elevation, if sensors are detecting different temperatures, that is indicating a cage misalignment, rebar cage misalignment. So I'll show you some typical the data and discuss on how we can interpret this test data. Okay. So two methods are available, as I said earlier. Method A is available in Sri Lanka. It's less expensive. We can make use of cross-hole sonic logging tubes. Okay, or you may have to drill if you are planning to use method A. And this test is conducted when the tubes are dry. You can't have water in the access tubes, right? So you must remove water before conducting this test. So then a probe is slowly lowered along the access tubes at a rate given by this 0.15, less than 0.15 meters per second, and start taking temperature readings along the tube. And this test can be done similar to the cross-hole sonic logging test. Using different access tubes, you take the temperature readings. The second method is using the wire method, thermal wire method. So in this case, the wires are fixed to the rebar cage, right? So after the wires are fixed to the rebar cage, you can't reuse them. So the wires have to be compromised, okay? So along the wires, for every 300 millimeter, there is a thermal sensor, right? Every 300 millimeter, there is a thermal sensor, and typically we are using a minimum of 4 wires, right, along the rebar cage, diametrically opposite to each other. Then these wires are connected to a data acquisition port. It's known as tap box. This tap box can be removed after the test and you reuse, but the wires cannot. Wires are permanently embedded. Okay. So this is the probe method, method A. And this is the probe. You can lower the probe along the access tube, and there is an infrared sensor. This is detecting the temperature, right? And you can measure the depth also. So some photos showing the test, right? Yeah, this is the wire and this is the access tube. So the probe is slowly lowered to the bottom of the tube and starts taking temperature readings. Right? So this temperature, these are the 4 access tubes, and you can, similar to the cross-hole sonic logging test, you can insert the probe through each tube and take temperature readings, right? Yeah, this is a picture showing the probe and the access tube. Right, this is method B. Method B, the thermal wire method. This is the wire with the sensor, thermal sensor. So every 300 millimeter distance, you can see the sensor. And this wire is fixed to the rebar, right? And the wire, the end of the wire has to be connected to this the data acquisition port, tap. And this is connected to the data logger, right? Yeah, this is the wire already fixed to the rebar cage. So it is necessary to have at least 4 wires diametrically opposite to each other, right? Like this. So these sensors starts detecting the temperature along the pile. Right. So this figure is showing the temperature during heat of hydration with the time. So you can see 4 curves. So each representing a different pile diameter. So this is the largest pile diameter. So when the pile diameter is large, the temperature rise is also large. Okay. For small diameter piles, the temperature rise is less. So the best window for the test is after 12 hours. So you can see after about, this is x-axis is hours, indicating the hours. So after, say, for about 12 hours, right, up to about, let's say, for large diameter piles, you can go up to about 72 hours. This is the best window for conducting the test, because during this period, you can see the highest temperature rise, right? The highest temperature rise. For relatively small diameter piles, this is the testing window from maybe 12 hours to 36 hours, right? 12 hours after concreting. You can start the test 12 hours after concreting and continue the test up to 36 hours. So this is this testing procedure is quite fast compared to sonic logging. To conduct the sonic logging test, you have to wait for about 3 days minimum. But TIP test, thermal integrity profiling test, can be conducted 12 hours after concreting, right? And this purple color zone indicates the optimal testing window, best window for testing. So the coverage of the testing area, the GGL means gamma logging. I have not discussed this. This is not popular at all in Sri Lanka, and it has a very low testing coverage. You cannot detect any defects within this region using gamma logging, and it is actually using radioactive material. Therefore, this is has some health hazard as well. So this is not popular in Sri Lanka, gamma logging. But cross-hole sonic logging is popular in Sri Lanka. You can detect any defect within this region, right? Outside the cage, you cannot detect any issues. But the thermal integrity profile, TIP test, has 100% testing coverage. You can detect any defect within the cross-sectional area of the pile. So this is a typical, now let me explain you on how to interpret this data. This is a typical temperature profile taken along a wire, or maybe after inserting a probe, you can detect the temperature at different depths. This is a typical record, right? So you can see if the pile has a uniform cross section like this, the uniform cross section, then the temperature must be uniform along the pile. Close to the top and the bottom, you will see some reduction in the temperature because this area is exposed to the surrounding air, right? So it is exposed, no soil cover. So as a result, heat will quickly dissipate. As a result, you will see a sudden drop in the temperature close to the top and close to the bottom also, because you have soil, surrounding soil. So through soil, heat will dissipate very fast. So as a result, you will see some reduction close to the toe as well. So bottom roll off and the top roll off are quite common in this kind of temperature record because of the fast dissipation of heat. But within the pile shaft, you should detect a uniform temperature profile like this, constant temperature profile, right? So this is the record taken from one wire. So if you have 4 wires, all 4 wires must indicate the same temperature profile, identical temperature profile if there are no defects, right? But it is not the case if there are issues. Now let me try to interpret this record. So temperature records with the depth, right? Now if you take a cross section taken at the 40 feet depth. So these are the different wires. How many wires? 1, 2, 3, 4, 5. I mean, large number of wires are there, right? So these are the wires indicating the wires, sensors. And you can see this is the cross section. This is the cross section taken at 40 feet depth. This sensor is measuring the highest temperature, close to 160 degrees. And at the same depth, this sensor is detecting the smallest temperature. So that means smallest temperature means this sensor is away from the center. It's close to the surrounding soil. That is why the temperature is less. Energy has already dissipated. Heat energy has already dissipated fast. Right? This particular sensor is close to the center. That is why you detect a higher temperature. So this is clearly indicating some misalignment of the rebar cage because these sensors are fixed to the cage. Fixed to the rebar cage. Right? So by looking at the different temperatures, you can plot the alignment of the cage like this. Similarly, for other depths also, you can plot the alignment of the cage, and the analysis software can give a three-dimensional diagram of the cage, rebar cage, right? Then another record, sorry. This one. So again, you can see some cage offset, different sensors indicating different temperatures at the same depth, means that the cage is misaligned. But in this region, there is no misalignment. Here again, some cage offset misalignment. With this region, again, no issue, right? Likewise. And in addition to that, you can see compared to the average temperature, there is a temperature increase in this particular region. So this is indicating a bulging. So if you have bulging, there is a large concrete cover. So higher concrete cover means it takes much longer time for the temperature to release its energy, right? Heat of hydration. So this is indicating a bulge. Same here. Higher temperature, right, compared to the average temperature indicates a bulge. And there is a cage offset also. So you can see different temperatures at the same depth. So there is a cage offset as well as bulging. Both defects are there. For this one, so there's no significant bulging. You can see almost uniform section, but here there is a significant increase in the temperature. It is indicating a bulge, but no serious cage misalignment in this case. Bulging is there. Similarly, there can be a necking or reduction of the pile diameter. In that case, if there's a reduction in the pile diameter, the heat will dissipate fast. So as a result, you will detect a smaller temperature, right? So then the results can be presented in this kind of profile. Okay, the software is capable of presenting the results in this kind of three-dimensional profile. So indicating bulges, necking like this. This is indicating necking. Okay. Small temperature means if you have a sensor here, it dissipates energy faster than this sensor because of the small cover. Okay. So this is a real test data. You can see significant cage misalignment. So different sensors at the same depth indicates different temperatures, means cage has a misalignment. Then there is a serious necking, very serious necking. So this is the three-dimensional profile. You can see the exposed rebar cage in the diagram, and this pile, a core is drilled to further investigate, and the drilled core is shown here. You can see poor quality concrete, right? The honeycombing due to poor quality concrete. So this kind of defects can be identified by the thermal integrator. So it's a very versatile test with a lot of applicability. Then let me discuss on the high strain dynamic load test. Right. So high strain dynamic load test is again the idea is sending a stress wave and detect the response. So the difference between the high strain dynamic load test and the PIT test. PIT test is also the principle is quite similar. So you are giving a small hammer blow and detect the response using the accelerometer, right? But the hammer blow will send a stress wave with a low strain. So it is also known as low strain dynamic load test, PIT test. But in the high strain dynamic load test, a heavy blow is given, right? Heavy blow is given as an impact load. And then the response is detected by two sensors. One is a strain gauge. The strain gauge detects the strain along the pile. And this one is the accelerometer. So accelerometer is detecting the acceleration of the particles, right, during the propagation of the wave. So these two, it is recommended to have at least two sets of sensors diametrically opposite to each other. So you have another set in the other side of the diameter, right? For large diameter piles, four sets are used. Generally, four sets are used. The sensors are fixed at a depth below the top of the pile to prevent any damage to the sensors. And sometimes if you fix these sensors close to the impact, then it may not detect the impact very well. So therefore, it is generally recommended to install these sensors at a depth 1.5 times the pile diameter or 3 times the pile diameter below the top of the pile. Okay. The analysis, let me explain you the analysis. I'm not going to go into the detailed theoretical explanations. So in order to explain, to understand the interpretation of this test data, you have to have some idea about the wave propagation theory. So, but I'm not going to explain that in detail. Let me quickly explain the concept behind the analysis. So the strain gauge is basically detecting the strain. So strain can be converted to a force by using the Hooke's law, right? F over A is the stress. Stress is equal to elastic modulus into strain. So elastic modulus is the elastic modulus of the pile material, concrete or steel or whatever, right? So you can basically obtain the force, right? Force propagating through the pile using the strain gauge with time after the impact. Then the accelerometer is measuring the acceleration, particle acceleration. So acceleration can be by using the acceleration time record, you can get the velocity, particle velocity, right? When you integrate the acceleration with respect to the time, it gives the velocity. Then the velocity, the particle velocity, we can prove that the strain is equal to delta L O L, the change in reduction in the length due to the impact by the original length of the pile. The change in the reduction of the length due to the impact is caused by the particle velocity. So Vt, V is the particle velocity, Vt is delta L, Ct, C times T, C is the wave velocity. So wave velocity, it's not the particle velocity, yeah, wave velocity along the pile into T gives the length. Ct is the length. So we can prove that the strain is equal to V over C, particle velocity divided by wave velocity. And you can simply replace V over C here. So AE times V over C. AE over C is the pile impedance, right? As I have explained earlier, AE over C is the pile impedance. So velocity is detected by the accelerometer. So accelerometer gives the velocity. When the velocity is multiplied by the pile impedance, it gives the force. So both sensors are right. Both sensors can be used to detect the propagation of the force. Strain gauge is directly measuring the force. Yeah, like this. Accelerometer is indirectly measuring the force by velocity, by measuring the velocity. So both sensors are detecting the propagation of the force. So keep that in mind. The testing procedure, let me explain the testing procedure. There are different testing procedures. This pile dynamics incorporated method, PDI method, is the widely used technique is in Sri Lanka. There are other methods as well. They are not popular in Sri Lanka. We don't have a lot of experience in this TNO procedures embed method. Pile dynamic incorporated method is the widely used analysis technique in Sri Lanka. So the instruments should be installed, as I said earlier, instrument must be installed at least 1.5 pile diameters below the pile top to avoid any end effects. A minimum of 2 accelerometers and 2 strain gauges must be attached diametrically opposite to each other. So large diameter ones, you need at least 4 sets, right? So you have to make sure that the section that is used to attach the sensors is free from any defects, right? It should have a uniform cross section, no material quality issues. Otherwise, the interpretation becomes very, very difficult. So you have to select a proper section for the installation of pile. Usually, we build up the pile. We build up the pile and then install these sensors. Right? Then the testing procedure. This is this figure is showing the testing setup. So the hammer is shown here. The weight of the hammer is usually taken as equal to 1% to 2% of the test load. So let's say you are planning to test the pile for a test load of 10,000 kilonewtons. You need to have a weight of 100 kilonewtons to 200 kilonewtons. That means 10 tons or 20 tons. Hammer is needed, right? For large diameter piles, better to go up to 2% of the test load, the weight of the hammer. And you need this kind of guard rail to guide the drop of the hammer. Otherwise, there can be eccentric impacts. So eccentric impacts can affect the response, pile response, and pile can undergo bending also, right, due to eccentric impact. So we must try to prevent that. The testing procedure is quite simple. First, a small blow is given to check the quality of the instruments, right? A small blow is given and the response is analyzed to see if there are any issues with the sensors. So if we do not detect any issues with the sensors, we keep on giving the blows by increasing the drop height. For each drop height, you can calculate the mobilized capacity of the pipe. Mobilized means in order to maintain the equilibriums, the pile must mobilize a certain capacity. That capacity can be calculated by the analysis tools. So you keep on giving increasing the blows until the mobilized capacity becomes equal or greater than the test load. So that is the testing procedure, right? So I told you that we need to check the quality of the instruments. So this is a typical wave record. I told you that we are using a number of sets. So this is average response. Okay. So average force response taken from the strain gauges. This is the solid line represents the average force response. The dash line represents the average velocity response. So velocity actually using the accelerometer. So accelerometer is measuring the acceleration, and that can be converted to velocity, and the velocity when you multiply it by z, it gives the force. So both these diagrams are basically giving the force, showing the force, but one curve, in one curve, the force is measured using the accelerometer. In the second one, force is directly measured using the strain gauge, right? So if let's say the pile is having a uniform cross section and there is no soil resistance, both these records should indicate identical response. But it is not the case because of the soil resistance. Because of the soil resistance, you will see a separation of the two curves, right? After some, maybe after some depth, but at least up to the first peak, right? Up to the first peak, there is no soil. No? The sensors are installed at a depth where there is no soil. So at least up to the first peak, the response given by both the accelerometers and the strain gauges must be identical to each other, right? After that, when the waves enters the soil, then there can be separation like this. So this is indicating good quality data. Now this one, the right hand side figure, is indicating a poor quality test data because F and V are not proportional. Force record and the velocity record are not proportional. At least up to the first peak, they must show proportionality, right? It is ideal if you can get identical response, but sometimes you might not get identical response, but the responses must be proportional to each other. But here they are not proportional, that is indicating poor quality data. So when you see this kind of response, you must indicate the records of individual sensors like this. So this is the average response, is indicating non-proportional data. Once you encounter non-proportional data from the average records, average force records taken from different sensors, average velocity records taken from different sensors, right? So this is the individual record. So force records of from two opposite strain gauges. So you can see very totally different response. Then the velocity records obtained from two opposite accelerometers are very uniform. I mean, identical to each other. So accelerometers are working perfectly, but the strain gauges are not working well. So there must be something wrong with one strain gauge, possibly due to a loose strain gauge. So you have to check the quality of the instrumentation. Okay. Then these records, the records shown on the right hand side, you can see up to the first peak, identical response. Then after that, there is a separation. So this is indicating good quality test data. This one, the force records, right, from two opposite strain gauges are not equal to each other. They are proportional to each other, but you can see the same pattern, but they are not identical. This is indicating a bending of the pile. So one sensor is detecting a higher force, the opposite sensors are detecting a lesser force. So this is probably due to pile bending. So the impact is not concentric, it is eccentric, most probably, right? Now let's see how we can interpret this data. So this is a typical force record and velocity record. Okay, so you can see up to the first peak, both force and velocity records are identical, almost identical to each other. Then there is at a certain depth, right? Certain depth below the pile toe. So I mean the wave, when you apply the impact, it sends a stress wave. The stress wave propagates at a velocity given by c. C is the wave velocity. So the L over C, L is the length of the pile, right? If you apply S equals ut, S is equal to L, the length of the pile, right, is equal to velocity, the wave velocity, which is c into t. So L divided by c is the time taken for the wave to travel to the toe of the pile, right? So wave, now we are detecting the reflected wave. So for the wave to travel to the toe and to come back, it needs 2 times L over C time. This much of time is needed, right? So this is the time taken for the wave to go to the toe and come back. So before this happens, within this time period, if you see some kind of separation, it can be either due to a defect or due to the mobilization of skin friction. If the velocity record goes above the force record, right, like this. Now you can see the dashed line is velocity response. Solid line is the force response measured by the strain gauge. So if the velocity overshoots the force response, this is indicating a defect along the pile. Maybe this sudden overshoot may be due to a crack or joint along the pile. Then you can see after certain pile depth, force is increasing, velocity is decreasing. Velocity record is gradually decreasing, force record is gradually increasing. This is due to the development of the skin friction along the pile, right? So this is indicating the mobilization of skin friction. Okay. So let's have a look at some typical PDA records. So you can see up to the first peak, the force record and the velocity records are coincide, identical to each other. Then after certain depth, skin friction starts to mobilize, and close to the pile toe, velocity overshoots. Velocity is gradually increasing while the force is gradually decreasing. So this is indicating a soft condition close to the toe. Higher velocity always indicate that there is a soft condition at that particular depth. So then this one, the thin line represents the force record. The thick line represents the velocity record. So you can see up to the first peak, both are identical. Then after that, the two curves starts to separate. But the force record is always above the velocity record. This is indicating the mobilization of skin friction. So it's a good quality pile, and close to the end of the pile, significant increase in the force and the significant reduction in the velocity. This is indicating that the pile is resting on good end-bearing strata, right? So this pile will mobilize a significant end-bearing value. Then let's have a look at this one. So this is the travel time. So before the wave goes to the pile toe and come back, there is a sudden increase in the velocity, right? The solid line, the thick line indicates the velocity. So sudden increase in the velocity means there is a defect. But the pile is actually resting on good quality strata because the force record is always above the velocity record close to the pile toe. So no soft toe condition or any other issue, but somewhere in the middle of the pile, there is a defect, right? So let's try to interpret some more PDA test data. This one. So you can see force record is always above the velocity record. Very small defect is there. Maybe this is almost negligible. And close to the pile toe, the force record shows a sudden increase, and the velocity record indicates a sudden decrease. So this is indicating that the pile toe is resting on good quality data, good quality strata with a high end bearing value, and no integrity issues. Always the velocity is smaller than the force, right? Second one is, I think, almost identical to the first one. This one, you can see after the first peak, there's a significant increase in the force even before the toe, and significant reduction in the velocity. That means the pile is mobilizing a very large skin friction, right? So this is a very good friction pile. This is indicating a very good skin friction, mobilization of skin friction. Then let's have a look at this one. So this is the length of the pile, travel time representing the length of the pile, and you can see velocity goes up. This is the velocity response goes up while force suddenly drops. This is indicating a defect. But it is an end-bearing pile. So close to the pile toe, you can see a sudden increase in the force. This is the one that we discussed earlier. And this pile has multiple defects. So before the wave goes to the top, you can see sudden increase in the velocity, indicating a defect. Close to the pile toe also, you can see sudden increase in the velocity, right? Velocity record is given by this dash line. So you can see sudden increase in the velocity and sudden decrease in the force, indicating a soft condition at the close to the toe. So this is not a good quality pile, right? So I hope you can interpret the typical PDA test data. The mobilized skin friction can be calculated by this difference. So this is the force measured by the accelerometer, sorry, strain gauge. This is the velocity record, the force, estimated force by the accelerometer. So this difference, right, it can be proved that this difference is equal to the mobilized skin friction, Rs. Have time? Yeah, okay. So how can we now I have explained you on in the previous slides, I have explained you on how to detect any integrity issues using high strain dynamic load test data. So not only integrity issues, we can estimate the capacities as well, pile capacities, by referring to the high strain dynamic load test data. The PIT test data cannot be used to measure the capacities. PIT test data can only be used to detect any integrity problems, right? But the high strain dynamic load test data can be used to estimate the mobilized capacity as well. So this is the static pile capacity given by the PDA test record. JC means that it's known as the case damping factor. This case institute is the institute that develops the analytical methods for analyzing the PDA test data. So that is why this damping factor is known as the case damping factor, right? And this capacity, this R static, is known as the case global capacity. Global capacity. And the typical value used for JC is around 0.4 or 0.5. Okay. Then F1 and ZU1 represents these two values. F1 means the force measured by the force record. ZU1 is the force measured by the velocity record, right? Then this is representing the pile toe. So F2 ZU2. So if you know F1 ZU1 and F2 ZU2, by using this equation, you can calculate the pile capacity, mobilized pile capacity. This can be calculated in real time during the test, right? So this capacity is used to check whether the pile has mobilized the required test load. Okay. If the mobilized test load is, the required test load is mobilized, then we can terminate the PDA test. So this method, if we are using the peak values, right? If as F1 and ZU1, the peak, the values at the peak, then this is the time taken for the wave to travel to the pile top, pile toe and come back, right? T1 plus 2L over C. This time, this gap is 2L over C. So this is representing the toe of the pile. So if we are using the first peak as F1 and ZU1, the capacity calculated using the two peaks is called the RSP method. And sometimes, right, it is noted that the first major peak, this one, first major peak may underestimate the mobilized pile capacity. That means before, at this particular peak, we assume that the wave is traveling close to the sensors. That is why you detect a peak. But there can be a certain delay, right? There can be a delay. As a result, these two values may not represent the sensor locations sometimes. So therefore, in the estimation of case globe capacity, what they do is they change the T1 time, right? T1 time, and as a result, T2 will also vary. T1 and T2 will be varied until the maximum value is achieved by this equation. That is called RMX method. Okay. And it is noted that this value given by the RMX method represents the real capacity more than the RSP method. Okay. So if I explain this RMX method, it is like this. So same record, same wave record. So you vary the time T1. As a result, time T2 will also vary because T2 is equal to T1 plus 2L over C. So T1, T2 will vary until, and this is F1 ZU1, F2 ZU2. Substitute them here in the equation until you get the maximum capacity, right? So we are varying this T1, and as a result, F1 ZU1 will vary. F2 ZU2 will also vary. So we will vary this until the maximum value is achieved. That is called the RMX method. Okay. This is a typical field test data. So you can see drop number 1, drop height 600 millimeters. This is used to check the instrument quality. And after applying this drop, you can calculate the RMX value, right? Using this previous equation, this is take maximum mobilized capacity, right? Set means after the drop is applied, right, pile will settle permanently. This permanent settlement is set. Then in addition to the RMX value, we can also estimate the maximum compressive stress, maximum tensile stress, and the maximum force transferred to the pile. These two values can be checked with the allowable compressive strength and the allowable tensile strength of concrete or steel or whatever pile material. So we must make sure that these two values should not exceed the allowable stresses. And this is the mobilized capacity. So when you keep on increasing the drop height, you can see the pile set will also gradually increase. And as a result, RMX value also will increase. So finally, 9,510 RMX value is reached. I think that this is more than the required capacity, right? So if this is more than the required test load, we can stop the test. So this is a typical field test data, right? RMX value is calculated in real time. So this is what you can get from the PDA after conducting a PDA test. So you can see pile details, right? The length of the pile and the test load. Working load is 690 kilonewton. Test load is 1.5 times this one, right? For a working load test. Usually we conduct the test up to 1.5 times the working load, right? For ultimate load test, we can load the pile until failure, right? Sometimes 2 times the working load, or sometimes in some cases 3 times the working load. So the wave speed, the density of the material, length of the pile, these details are given. Then the hammer details, right? The weight of the hammer, the hammer stroke, and the test date, the results, PDA results, RMX value, mobilized capacity, maximum force, compressive strength, compressive stress, right? The pile integrity also can be obtained by the minimum pile integrity is 98%. That means everywhere else the pile integrity is more than 98%. So it is having a good integrity along the pile. So only 2 blows are given. Then this is important, CAPWAP analysis. So CAPWAP analysis is done at, we cannot do it in real time. After conducting the PDA test, we will take the results and analyze them in the office using a signal matching technique, right? So we are using a CAPWAP software. CAPWAP means Case File Wave Analysis Program. This is again developed by the Case Institute. So that is why it is known as CAPWAP software. So using the CAPWAP software, we can analyze various other characteristics of the pile, like the skin friction, right? End bearing. Not only that, you can get the skin friction at different depths, mobilized skin friction at different depths, and the pile load settlement curve also can be obtained by CAPWAP analysis. So if I quickly go through the CAPWAP analysis, I'm not planning to do a detailed explanation on the CAPWAP analysis, but let me quickly go through this signal matching technique. So in the CAPWAP analysis, what we basically do is the pile is divided into large number of segments like this, right? Pile is divided into segments. Then the entire pile is represented by this kind of lump mass model. The hammer and the cushion, driving cap, the pile, these are also modeled as lumped masses, and the contact between each segment is represented by springs. So this is representing this pile segment. This is representing the second pile segment. So pile segment to segment contact is represented by the spring. Then the pile is in contact with the surrounding soil, right? So soil pile interaction is represented by this spring and the dashpot. So dashpot will represent the damping characteristics, the energy absorption, right? Damping characteristic. This is representing the elastic response of the soil, right? So this is basically representing this spring, and this dashpot is representing the soil pile interaction. And this spring is representing the pile to pile interaction, right? So likewise, this is divided into large number of segments. Then for the soil pile interaction, there is a model like this. This is the model assumed by the first person who proposed this signal matching technique. It is Smith. In 1960, he proposed this analysis technique. So this is the force displacement response or force displacement relationship proposed for the soil pile interaction. So you have a linear response up to a certain displacement, and after that, it will reach the ultimate resistance. Ultimate resistance means ultimate skin friction for a particular segment. For each segment you have a different curve. You might have a different curve depending on the soil type. So this segment may be surrounded by sand. This segment may be surrounded by clay. Likewise, you can have different soil surrounding the piles. No? So if you have different soils, you will have different curves like this. So each pile segment, there is a model like this, right? So this is the toe response. So Smith assumed the pile toe response is something like this, right? It will not go to the negative side. Can't go to the negative side. But the skin friction can go to the negative side, plus minus both sides, right? And up to a certain displacement, the soil behaves as an elastic material. So this displacement is known as the quake. QUAKE, quake. So this is the skin quake because this is representing the skin friction. And this is called the toe quake because this model is representing the behavior of the toe. So by assigning this type of response for each segment, right? By assigning that this kind of different response for each segment, you can calculate the pile response for a given hammer blow, right? You have already have a measured response. By using the sensors, by using the accelerometer and the strain gauge, you have already measured the actual pile response, force response. You have already measured. But by using this analytical model, you can calculate the pile response, right? Force. So what this CapFab software does is it will calculate the pile response and compare it with the measured response like this. Sorry, I will come to that later. Yeah, this is the force measured using the strain gauges, the solid line, force computed using CapWeb software using that analytical model. Definitely they will not match, right? Because you are making so many assumptions here now. This QM is an assumption, this R ultimate is an assumption, but actual pile response is not a curve like this. It's a non-linear response. So definitely you will not get a perfect match, right? Then what the software does is software will start changing all these parameters, QM, R ultimate, for all the segments. All the segments, the software keeps on changing the parameters until there is a perfect match between the measured response and the calculated response. This is what the software does. Okay. So after doing that, after doing the CapWeb analysis, you will get this kind of almost perfect match between the measured response and the CapWeb response, calculated response. So there is a statistical method to check the match quality. It is recommended to carry out this signal matching. This is called signal matching technique until a signal match quality less than 3 is achieved. Right? The software will tell you the signal match quality. So you have to keep on doing this until the match quality becomes less than 3. Right? Now that is the analysis technique. Smith, let me come back to this. Smith, this is the soil pile interaction model proposed by Smith. But later they found that this is not representing the real soil pile interaction response. This is also not representing the real toe response because Smith assumed loading, unloading to be to have the same the gradient like this. Loading ultimate and unloading ultimate, he assumed the same value, right? Loading quake, unloading quake, same value. But actually it is not the case. This is the current model used by the CapWeb software. This is the pile segment, this is the soil. So soil pile interaction model, the current one is something like this. So you have a loading response, loading quake, and this is the unloading response, which is different to the loading response. So two different gradients. And unloading quake is also different. Unloading level is also different. It's not the same as the loading ultimate. Similarly, toe response is also modified. They have introduced a toe gap to represent any soft toe condition, right? So this is the toe gap and the toe response. This is the unloading response. So quakes are different, right? This is the current model. Actually, the current actual model is something like this. This is what I have explained earlier, right? Loading, unloading, they are different gradients. This is the unloading quake. This is the loading quake, right? The unloading stiffness, unloading stiffness. This is the current soil pile interaction model used in the CapWeb software. They keep on improving this actually. Yeah, this is the current one. Similarly, for toe response, this is the one that is used by them in the software. They have introduced this gap, and the loading response, loading stiffness and unloading stiffness are different. As a result, the quakes are also different, right? So the software is now using these models, and until there is a perfect match, the software keeps on changing these values. Ultimate values, the stiffness values, the quake values, everything will change by the software until there's a perfect match. This is almost impossible to do manually. It can only be done by a computer software at the office. You can't do it in real time. During the test, you can't do this. Huh? You have to, after the test, you have to take the wave records to the office and do this. It takes some time. So once this is done, right, the computed one, there's a perfect match between the computed one and the measured one. The computed one, first computed using CapWeb software. Now you have finalized these values. What is the ultimate skin friction? What is the quake? Everything for each segment. There are large number of segments, huh? Like this. For each segments, you, after the perfect match is obtained, you know what the ultimate skin friction, what is the skin quake, likewise. All the details are known. So from that, we can obtain the mobilized skin friction values. This is a typical CapWeb analysis result summary. So you can see piles, soil segment number 1, 2, 3, 4. That means this pile is divided into 16 segments, right? 16 segments. Do I have? Yeah, okay. 16 segments. And for each segment, the mobilized skin friction values. You can see the mobilized skin friction value for each segment. Quake values, right? Quake values, force, the ultimate, the skin friction values. Likewise, all these records can be obtained. And by analyzing the toe response, you can get the mobilized toe, the end bearing value. Okay. And not only that, we can produce this load settlement curve. This load settlement curve is equivalent to a static load settlement response. Static load settlement response, right? We can get you can see two curves. One is representing the pile top load settlement behavior. This one is showing the pile bottom load settlement behavior. So this is equivalent to a static load test, equivalent to conducting a static load test. So you can see PDA test is very versatile test, and it has a lot of applicability in the analysis of the pile capacity. So I don't know whether I have to stop now. It's almost, the time has already passed. Vishal, shall I continue? Hello. Can you hear me?
Yes,
Yes.
sir.
Okay. I need about 10 minutes more. Is it okay if I continue, or shall I stop because time has already passed, I guess?
Sir, it is we can stay 10 minutes, sir.
Okay, okay. Let me quickly go through this, right?
Okay, thank you.
Right. So, so after that, let me discuss on MLTs, maintain load test. I am not going to explain. I will share this presentation with you, so you can go through it and easily understand the details given here. So let me explain the test procedure. Sorry. So the in the maintain load test, the pile is, this is the pile. Pile is loaded using actually loaded using cartilages. Concrete cartilages are used. This is the loading platform, and you can see hydraulic jacks and a loading frame. So the pile is loaded against this loading frame, and we will take the displacement measurements, right? So the more advanced version of this test is the instrumented pile load test. In the instrumented pile load test, the pile is instrumented with strain gauges. Okay, pile is instrumented with strain gauges at different levels. So I will show you some typical arrangements of MLT platforms. You can go through it. I don't have to explain this in detail like this, right? So in the instrumented pile load test, the pile, after identifying the different soil layers, so it is better to have a borehole first. Then you know the layer thicknesses, soil layer thicknesses. So to represent each the soil layer boundary, we can have a strain gauge. So here you can have one set of strain gauges. There you can have another set of strain gauges. Here you have another set of strain gauges. So these are representing the layer boundaries. So once you conduct the test, each strain gauge uh, at each strain gauge level, it is measuring the strain. So the difference in the strains at different levels, if you know the strain difference, you can convert the difference in the strain into a force by using the Hooke's law, right? Stress is equal to elastic modulus into strain. So if you know the strain difference, you can calculate the force difference. That force difference is indicating the mobilized skin friction. So by conducting an instrumented pile load test, you can get the skin friction mobilized along the pile, right? So these are different types of instruments used along the pile. The embedded strain gauges can be either attached to the rebar cage, or you can even weld them, right? Cut some sections of the rebar cage and weld the strain gauge into the rebar cage. That can be done. So I'm not going to explain this the testing procedure. This is the the loading schedule. So first you have to apply the 25% of the working load, then increase it to 50, 75, 100, then unload it, then load it again up to 150%. If it is a working pile, we load up to 150 times the working load and unload. So this is done in 2 cycles, right? And at each load, you have to hold the load for a holding time of 1 hour and so on. So different holding times are shown here. This is the loading schedule given in the CEDA guidelines, okay? It's old, I mean, the previous name is ICTAD, now it is called CEDA. So CEDA guidelines are shown here. This is IC guidelines, IC UK guidelines, okay? Design verification load, 25% of the design verification is quite similar to CEDA. The design verification load is the working load plus 2 times the negative skin friction. If you have negative skin friction, you have to add 2 times that to the working load. And 25% is applied first, then 50, 75, likewise. It is done in cycles. Acceptance criteria. So according to the CEDA guidelines, to accept a pile, it must satisfy these given the criteria. When the pile is loaded up to 1 times the working load, the maximum allowable settlement is 12 millimeters. And once you release the load, the net settlement should be 6 millimeters or less. And if the pile is loaded up to 1.5 times the working load, 25 millimeter settlement is allowed. And once this load is released, the net settlement should be less than 12 millimeters. So this is the acceptance criteria for a maintained load test. The Australian guidelines have slightly different values. Under the serviceability load, that means 1 times the working load, 15 millimeter settlement is allowed after removing 7. 1.5 times the design load, they are allowing a much larger settlement than the value specified under the CEDA guideline, 50-30. Then they have a acceptance criteria for high strain dynamic load test as well, which we don't have in CEDA. CEDA guidelines, there is no acceptance criteria specified for high strain dynamic load test, but there is an acceptance criteria given in the Australian guideline. So under the serviceability load, 12 millimeter settlement is allowed. Under 1.5 times the design load, 35 millimeter. So these values are given in AS 2159 1995 guideline. The recent one, 2009 guideline, has a slightly different values. So I will skip this. Once you do the load, the MLT test, this is what typical test record. You load up to 100% of the working load, unload it, then reload it up to 150 times the working load and unload it. So 2 loading cycles, right? We can get the ultimate the pile capacity using this load settlement curve. So there are different methods, DBA method, Fuller and Hoy method, Davison. Likewise, so many methods are available to obtain the ultimate pile capacity. Let me explain this Davison method because it is widely used. It is the most widely used technique. So Davison said that you draw a line represented by this equation. So 4 plus DO, D is the pile diameter, divided by 150, sorry, 120. Let's say your pile diameter is 1200. So 1200 divided by 120 is 10 millimeters. So 10 millimeters plus 4 is 14 millimeters. This is the elastic compression or elastic shortening of the pile due to the applied load, P. So when you increase the load, this P will increase. As a result, there is a gradient due to this P. And 4 plus DO at 120 is the offset, right? This is the offset. So you draw a line given by this equation until it meets the load settlement curve, and that will give you the ultimate load. That is the Davison, the failure criteria. According to the Davison failure criteria, this is the ultimate load of the pile taken as the ultimate load. Other methods will have different techniques for analysis. Okay, so I will not go into the details of those. I will skip this. This is the O cell test, or it is, in other words, it is known as the bidirectional load test. So here, during the installation of the pile, we installed this cell. It's known as the Osterberg cell. And after the pile is constructed, you can, using hydraulic jacks, you can apply load on both sides of the pile until failure. So this side of the pile, if it fails, it will give the ultimate skin friction. If this side of the pile fails, it will give the ultimate end bearing, right? If you place the Osterberg cell somewhere around at a location where the skin friction becomes equal to the end bearing, you can get both values at the same time, right? So you don't need any loading frame or anything, any sophisticated, expensive platforms are not necessary in the O-cell method. But this is not very popular for end bearing piles because in Sri Lanka we have mostly end bearing piles. So end bearing piles, end bearing is much larger than the skin friction. Therefore, this has limited applicability in this type of subsurface conditions. Okay, O cell tests. So these are the O cells. Some photos. So several O cell tests were conducted in Sri Lanka. Okay, several tests were done. Lateral load tests. I will not go into the details of lateral load tests. Finally, I would like to show you, I will skip this, I do not have time. I would like to show you a comparison of high strain dynamic load test results and the maintain load test results. So this is one test done on a pile. This pile is subjected to both instrumented pile load test and a PDA, high strain dynamic load test. So this is the blue color curve is the result of the instrumented pile load test, the actual load test. This brown color line is the static pile load settlement behavior obtained from the CAPWEP analysis. I told you that CAPWEP analysis can be used to get this curve. And you can see they are very close to each other. They follow each other very well. Okay. So I have compared this for many number of piles. This is another one, right? This is the MLT test. It's not an instrumented pile load test, but a maintained load test. The same pile is subjected to PDA test. And this is the response of both. So you can see there's a good agreement. This is another one. Similarly, this is some piles tested in Kalani area. Again, instrumented pile load test with this pile instrumented with this strain gauges. You can see the strain gauges here and the comparison. Right? Blue color line is the instrumented pile load test curve. Brown color line is the PDA curve. So PDA actually we have loaded the pile more than the instrumented pile load test because it's just a matter of giving a blow, heavy blow. But you can see they match quite well, reasonably well. So with that, I would like to stop the today's lecture. Sorry, there was some interruption. I think the number of participants exceeds the capacity, the Zoom capacity. But I hope you have gathered some knowledge. And if you have any questions or any comments, any clarifications, I'm free to answer. So thank you very much for giving me this opportunity.
Thank you so much, sir, for a clear explanation. So now we can allow for the Q&A session. So dear participants, if you have any questions, now you can ask.
So there are some questions typed in the chat box. Let me go through them. There is a question, how it will identify serious integrity issues. What do you mean by it? I'm not very clear about this. Okay. I think he's referring to some test, I guess. Okay.
Yes, sir.
Yeah.
Sir, I have one question. Sir, during some pile casting works, from 2 or 3 kilometers away from the site, for example, paddy field, the cement slurry can be coming out from the paddy field. Because so is there any way to rectify that issues?
Yes, actually, in this can happen due to the presence of some aquifer condition or due to the presence of some water flow through a cavity. This kind of problems are quite common in Kandy region, right? Close to the Mahavali River, there is surrounding the Mahavali River, you have mountains. So there is a flow towards the river always. And the rock type is limestone. It's crystalline limestone, marble. So through marble, there can be a lot of cavities. And these kind of problems are very common in Kandy region. So if you encounter this kind of issue, we can do several things. One is to have think of having a permanent casing, right? Casing all the way to the bottom of the pile. Another option is you fill the hole once you encounter this kind of problem, loss of concrete or a cavity. You can fill the hole, the drill hole, with low grade concrete, right? Low grade concrete, and let it stay for about 1 or 2 days. Don't wait for too long, then concrete becomes hardened and it becomes very difficult to drill. The purpose of having this low grade concrete is to stabilize the borehole, just for the purpose of stabilizing the borehole. So you can wait for about 1 or 2 days and continue drilling through the already poured concrete, right? That is another technique that can be used in this kind of situations. So quite expensive, but in some cases there's no other option.
Thank you, sir.
There's a question, any standard governing equation for classification AABB, or it's based on expert judgment? This is based on the experience and the expert judgment. Yes. There's another question. In which situation we need to request for thermal integrity profile test for large piles? Actually, thermal integrity testing is not readily available in Sri Lanka. It is very expensive at the moment. Particularly the thermal wire method is not used. It's quite expensive because once you embed the thermal wires in concrete, you cannot reuse them. It's gone, right? But we can use the probe method. Of course, we can use the probe method, and this thermal probing method has been used in several situations, but it's not very popular at the moment. But it has become a standard test method in countries like US, right? It's quite useful. I would say it is the future in integrity testing of piles, right? So very soon we have to adapt this technique. Okay. No, any questions? There is a question. Okay. During sandy soil or clay soils, piles can displace from testing. I think that this is what the question you asked, right? Piles can displace with testing. What are the remedies we can use in this situation? What do you mean by piles can displace? There are construction tolerances. For example, pile center can vary by 75 millimeters from the actual center. And pile inclination, piles can become slightly inclined, but there is a acceptable inclination, 1 to 75 verticality. So if you encounter a pile having an inclination greater than that, you have to reject the pile according to the Sri Lankan guidelines, right? If the center of the pile is more than 75 millimeters away from the intended center, it has to be considered as a reject pile. So in this kind of cases, you may have to you cannot rectify. There's no way of rectifying that this kind of casting problems. You have to have two additional piles and a pile cap to transfer the load. Then if the rock socketing length is 1.8 meters in one of the projects in Colombo, the required one is 2 meters. Is it okay, this rock socketing length? The rock socket length is usually given as a multiple of pile diameters. It is generally recommended to have a rock socket of at least 1 times the pile diameter. But if the rock is sloping, it is better to increase the rock socket length to 2 times or 3 times, and sometimes 3 times the pile diameter. And if the pile is going through very weak rock, in that case also we tend to increase the rock socket length, right? So there is no, you can't say hard and fast rule. If the rock is very good, you can and nearly flat, you can terminate the pile after having one rock socket of 1 times the pile diameter. Otherwise, we may have to decide on increasing the socket length. Then there's another. Is it possible to get low beta in a pile drilled through soft rock, but providing higher RMS larger than 2 times the required? A beta value actually is representing the impedance, right? So pile impedance, EA over C, the elastic modulus, cross-sectional area, wave velocity. Okay. So beta value will not be affected by the surrounding rock. But the capacities will definitely be affected by the presence of the surrounding rock. Beta value will be affected by the quality of the material, presence of any cavities, likewise. Okay. Why should we consider the pH indication during concrete pouring? You mean why we detect the, now it is directly affecting the corrosion of reinforcement. Okay. Okay. I think that's all. I will share the slides. No issue. I wanted to explain everything within the 2 hours. It's very difficult task. There are so many testing methods, and sometimes it's not just explaining the testing methods, and the interpretation may not be useful. You should know the theoretical background behind this. That is why I spent some time explaining the theoretical background as well. So I try to make it as concise as possible. Sometimes maybe it's too much for you. I will share the slides. No issue.